Good day to you. I'm Daniel Lee, and today I'll be explaining my pool game code as well as the pool game itself for my GMAPS project. Now, first of all, I'll give a demonstration of my game before I drop into the code and explain how it works. My game is able to use a pool cue with the distance based on the center or the position at which my mouse is clicked on the pool ball, and I'll pull with the end of the line following my mouse cursor. Then when I let go, the ball is able to move with the velocity based on the distance which the pool cue is pulled. Apart from these 5 brown objects are the enhancements, also known as slope fields. These slope fields will reduce the ball speed all the way down from its current velocity to 0. As the longer the ball stays within the thing, the closer the velocity gets to 0. However, because it's not set to 0, the player is able to move the ball out. Now, the ball, as you can see just now, there were also collisions between the multiple balls. Apart from that, balls are also able to collide with each other. Now, moving forward, it is difficult to probably aim a ball into the hole. What I'll be doing will be to send my white ball straight into the hole, and as you can see, the ball itself can be sent into the black hole to score, and as you can see, the ball is then set false, and then in a sense scored. Now that is all for the game itself. Well, we're mainly talking about the scripts and the functions. The first I'll be talking about the H-Vector 2D, which is my own in a sense vector 2 class. The H-Vector 2D has three variables within its constructor itself. And it also takes in an x and y, which 2 arguments. It has 4 different operators, which allow for specific either addition, subtraction, or multiplications between H-vector objects or a H-vector object with a scalar value. Apart from this, you can see here, there's also a specific functions which can be done. This uses the Pythagoras theorem to find the magnitude of a 2 H-vector units. And then there's also a normalize, which sets the magnitude itself to 1. This is normally used after magnitude, depending on what the user wants. There's also dot product, which is used to get the magnitude of the distance between a line to a point. While we also have a projection, which creates a new vector 2D, multiplying floats values created from dot product. And then using the formula, find for theta angle in a triangle. And then we find a theta angle here using the 2 values of the vectors that we already exist, or in this case, it's vector 2D. Then we return a value in radians. So for this, we do have 2 other functions which convert our H vector 2D to either vector 2 or a vector 3. Next, I'll be talking about the matrix. The matrix itself also has a bunch of constructors. This creates a multi-array, which we used where all H vector 2Ds are a 3x3 matrix. H matrix 2D are all 3x3. There are 3 ways to make a H matrix 2D. One is by setting an identity matrix, which will be seen later on. And then this would be to use a multi-array with a for loop. Lastly, it would be to, in a sense, hard-code it. Now, apart from this, first operator would be to add the matrices. This is very simple. Just to add the two entries of each one accordingly. Same for subtraction. Again, same thing. It's to take the entries and then subtract it. Now, for multiplication, this is done, for example, if it's a scalar, then it's very simple. It's like this, where all values are multiplied by the single scalar value. However, talking about vector 2D, then we just need to look at 0, 0, and 3, 0, 1, 1, 0, and 1, 1. As in a sense, H vector 2D, although we're only looking at a 2 by 2 as H vector 2D. If we look at it carefully, H is already fixed to a value of 1f, or a float value of 1. Now to multiply H matrix 2D by H matrix 2D, essentially use the formula that we already know. Because this is a 3 by 3 multiplied by 3 by 3 multiplied by 3 by 3, we get 3 by 3 back. It's essentially a fixed, in a sense, formula or method to multiply it. And all I've done here is just convert that into a code. Now, apart from this, for checking whether the two matrices are equal or are not equal, we just use a for loop, which we use a nested for loop, which takes one entry, check with the other entry, that one entry, and check with the other entry, so on and so forth, before returning either true by default, or if not all of them are matching, then we return false, and vice versa for this one, just to check whether they are false. Then moving forward all the way to identity matrix. This is very simple. Again, we use a for loop, and then if the specific entry is the same, equals where x and y are the same, then what will happen will be set to 1 if it's the same, and also be set to 0. This is just a more efficient method to type this entire code. If we speed this up a bit more, for matrix functions deal with the moving of the matrix itself or rotating the matrix itself. And as you can see just now, we were able to draw a line to shift our pool. What we do first is that we take the cursor's position on the world coordinate, and we check the position at which the pool cue, like the mouse cursor is at, upon pressing down, and then we check whether it's within the circle itself. We check whether the position is less than or equal to the radius of the ball. This means that the mouse position is within the ball itself. Then, if it is, then we allow the line to be drawn. Apart from this, the end of the line also follow the mouse cursor, assuming that the line already has been drawn. When it's released, what we want to do is we want to get the position of the mouse, and then convert that to a velocity value here. Then after I set the ball value, let's set that to the ball value over here. Set this to null so that the line will actually disappear after it's being used. As you can see here, the set to null will enable us to, the moment we release the thing, to remove the line itself. Now that that's in, I'm moving on to the ball 2D. So the ball itself, its position and velocity are set by H vector 2D. And it also has a coefficient restitution, which in a sense affects how bouncy the ball is. For the position, let's start with just set of positions, and then this left code here sets the radius of the ball to the radius of the sprite through the use of some simple math. And update ball physics. Velocity is set once per cue pool. Essentially, each time I drag the cue out and let go, that's when velocity is set. However, when there isn't like a new cue pool, then displacement is fixed, so the ball continues to move. Apart from that, we do want to add friction. So friction is this, which will constantly decrease the current velocity. And because velocity will change to a new pool, a new cue pool, setting the time for velocity to decrease to 0 based off time that will be most appropriate. Apart from this, we also have this function which checks the collision between the ball and the point, or the point on the ball circumference. The point checks whether there's a collision. Ball collision is done by getting the wall sprites and then setting the boundaries. So let's say we use the right wall as an example. This right wall here, we take the height, divide it by 2, and then this middle point will be, and then we add a bit more, this middle point there, if the ball value here is negative, because this is moving in the negative x-axis direction. If it's negative, that part would be, what we'll be doing would be to set that to, if it's essentially, if the ball head does exceed that area, then it's going to become, it means it has already collided. And this is done for the other balls as well. All these are done to check whether the ball is collided with another ball, the slope field, or the hole itself. Util is just used as a quicker way to find distance between two y-axes. Hole and slope field both use the same code, in the sense that essentially they just take the sprite radius, just makes it easier. And that for GM, this is used by just to be useful for debugging, where upon pressing R, the same will reload. Afterwards, we're talking about the table 2D. For table 2D, there be 3 nested loops. 1, 2, 3. The first one essentially handles ball checkers by selecting a first ball from here and then creating a second loop to check if this ball is equal to this ball. If it's not true, then we check whether the 2 balls are collided. This is running constantly because it's an update. By doing this, we can constantly check whether there's collisions between a ball and ensuring that we're not checking for the ball colliding in it with itself. For this part, we actually calculate whether the ball collides with the hole. Very simple. If it is, then we set the ball to false, creating a goal function. Then slope fields, this is where the velocity is set constantly downwards all the way to 0. Now for handlebar collision, what we're doing is that to get a ball collision, use formulas that we've converted from theory into code. Find specific values needed to put in, as explained in the code, which will be able to be seen later on when you are able to access the scripts that I'll set out. And then by doing this, we're able to get a specific value, which is unknown. So we want to get an unknown value first before we can find the missing value. That missing value is the direction and the magnitude at which the ball will move at after colliding with another ball. Adjust ball distance essentially just offsets the ball back to its original position if there's collided with an object. This is done by first finding the distance, afterwards shifting the ball continuously back to its original position. And that is all. Thank you.